I want to continue on this topic, the perturbation theory. Before I start with this new topics of perturbation approximation methods, I want to correct this. Our last lecture on trial variational functions. Okay.
Do you mind recording the lecture?
Okay. We have seen in our last lecture when we use two basis function. Okay. We obtain the ground state energy. Okay, so this is the ground state energy, the lowest energy, and the first excited state energy, which is the second lowest energy. Okay, sorry. So this is the approximate So this is the approximate value, and this one is the true ground state energy obtained from the exact solutions of Schrödinger equations for optical in one-dimensional box. Okay. We also have here, okay, solving this circular determinants. We can have here the energy, okay, for the second lower state and the exact energy, okay, for the second lower state. So this is the true ground state energy. Okay, both these energies are the true ground state energy. Okay, so we have this first and the second lowest state, second lowest state's energy. Now we are going to increase the number of basis functions, okay, from 2 to 4, F1, F2, and F3. Okay. Solving these circular determinants, okay, two block diagonals matrix, okay. These two block diagonal matrix, the first blocks and the second block, okay. So this is one of the block diagonal matrix. Okay. We got this energy, the approximate energy. So the second blocks, we got these two energies, 2 by 2 matrix, we got these two roots of energy. So we have here 4 basis functions. So we got here 4 lowest energies. So this is the true ground state energy from the solution of exact Schrödinger equations. This is the true energy. Using 2 basis functions, you can see here, by comparing this with 4 basis function, slightly improvement, this energy, we successfully lowering this energy from 002 to 0018, approaching to this exact energy 000, 002 to 0018, to this exact energy 000. At the same time, we also significantly here lowering this energy for the second energy 1.2935, this to 0.00, so we can see here very significant improvement here, 1.2 to 0.5, close to this exact energy, So theoretically, if we can include this infinite number of basis functions, this energy, all these energies, will approach to the exact energy, this exact energy, and we also can reduce this percent errors in our calculations. So after we obtain this exact this true energy, we can substitute, for example, these two energy into two simultaneous equation, two simultaneous equation from this selected determinants. The two simultaneous equation will be, this is one of the simultaneous equation with coefficient C 1 plus with coefficient 2. And also we can write the second equations, the second equations for these two simultaneous equation. The second equation. So we substitute this first energy, first roots into this equation and this as well here. Okay, the second simultaneous equation. Okay, so this is first root, and we have here two simultaneous equation. These two simultaneous equation, and we know these two simultaneous equation, the non-trivial solution. Okay, so this is the non-trivial solutions. Of these two simultaneous equation. Okay, we denote this C as C1, C2, C1, 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 C1. Okay, C11, C12, C11 here, C12. Because we have here 4 roots of energies. So we have here 4 set of C. Okay, we also here for 1 and for 2. Okay, so we have 4 set of C. Okay, so we can write here C1 and C1 in term of C2, C2 in term of C1. Okay, let's say we write C1 as K, so C2 will be in term, okay, we write here C2 in term of C1. Okay, because this is C1. Okay, applying these normalization conditions, okay, for one of these, okay, you can choose, okay, either this one or this one. Okay, okay, sorry, this is the two simultaneous equation. Okay, we are here referring to this two simultaneous equation. So this is the solution of these secular determinants. Okay, so this is the secular determinant. This is simultaneous equations. Okay, this is the simultaneous equation, one of the simultaneous equations. So now, okay, we can write this first set of, okay, C. Okay, first set of C. This C1, 3, and C1, 4 here is 0, right? And this as well. Here C1, C2 are 0. Here C1, C2 are 0. Okay. This is from the solutions. Okay. Whereas here C3. Okay, 0 here. So when we have this equation, simultaneous equation, of course, C3, C4 is 0. So the linear combination here, we only have here, okay, C1 and C2 only, okay, with C3 and C4 0. So this is one of the trial functions and gas function we want to determine, okay. So this is one of the trial function or gas function containing here F1 and F2 only, because C1 and C2 here are non-zero. So we apply the normalization constant to this phi 1, okay. So this is normalization, normalization conditions, not normalization constant, normalization constant, okay. You learn in physical 1, physical 2, okay, by setting up here this integral here to be 1, okay. So we know C1 and C2 here in terms of K or, okay, in other words here C1, C2 in terms of C1. So we can write here this overlap matrix, this overlap integrals, okay, these trial functions. So we write here, okay, this to be like this one. Okay, so now we can solve this, okay, two equation from here and this one. Okay, we know this K, okay, we substitute into this one, into here, okay. So finally we get this pi 1, okay, the trial functions for the first state of this energy, okay. So our approximate energy here is W1. So this state described by this, characterized by these functions, okay. So this trial function is the approximate wave functions for this state, okay. Likewise, you can find this pi 2, phi 3 and phi 4 using this 4, okay, another roots, okay. This first block, okay, we have here W1 and W2, okay, which is the solution of this one, this simultaneous equation. We have another solution for this, okay, second block of matrix. So we get here W3 and W4. So this will get here W1 and W2. The solution of circular equation, we get this one. After, okay, we get this W1, W2, we substitute into here, okay. You have seen this, okay, and this will, okay. Similarly, you can do for this W2, W3 and W4. So using these conditions, normalization conditions, okay, you can write this for phi 2, phi 3, and phi 4. Okay, so we simplify this equation, okay, by writing here, okay, x over L here as x dx. X here, okay, fix, okay, we fix the dimension of these potentials box, okay, varying only this W, X, okay, this distance. So we can plot this phi 1, phi 2, phi 3, and phi 4. So this is what the general formula for Trafalgar's function, where we can include this like this. Slater types orbitals. So this is Slater types orbitals. Okay. In our equation, you can see here the ground state. Okay, we want to find only the ground state for n16. Okay, of course. And basis function will get this n number of energy state. Okay, from this E1 to E16. So this is one of this. Sorry. The energy for this one. Okay, we want to compare this energy. This energy converge. Okay. Okay, nearly converge to this energy. Okay, for formant, if we consider up to the 5, this converge up to these 5 decimal places, 1, 2, 3, 4, 5. Okay, nearly converge the energy. Okay, which is close to the exact ground state energy. Okay, so if you can this include infinite numbers of basis function, okay, of course you will, okay, you will here be able to find this approximate energy approaching to the exact energy, which is 0.5. Okay, this is the exact energy. Okay, if you use this infinite number of basis functions. Okay, how to find this one? Okay, we know for the hydrogen atoms, okay, the ground state energy is 1, 2 in atomic units. Okay, so this is in atomic unit. In atomic unit, okay, in unit H3. Okay, this unit H3. Okay, so this in atomic unit. When we set here n is 1. Kenapa lambat ni weh? Baru bangun tidur ke? Okay. Okay. Next, so this is quite new, okay, for you. The perturbations theory. Okay. When we use this perturbation theory, when the Hamiltonian operator for the given problems, okay, slightly differ from the exact or true Hamiltonian operator. Okay, Please refer this first statements, okay, in this introductions. Okay. Slightly different from the given problems. So we can use, okay, all the informations from the exact solvable Schrödinger equations, the Hamiltonian is Hamiltonian operator, to solve these problems. Okay, so we have here these unsolvable Schrödinger equations. Let's say the unsolvable Schrödinger equation in one dimensions for n harmonic oscillator. Let's say for this n harmonic oscillator, we know the potential energy for the harmonic oscillator is kx square. So we here, okay, we add this cubic potentials. Let's say these potentials. So this n-harmonic systems, okay, this unharmonic oscillator, the Schrödinger equation here, the second differential equation here, okay, this is dx squared. Cannot be solved exactly. Because of this, okay, cubic potentials, okay, the Hamiltonian here slightly differ from these solvable Schrödinger equations. So the Schrödinger equation for this harmonic oscillator, we know, okay, consisting of this only quadratic potentials. So the difference here is only these terms, okay, the third terms in this Hamiltonian operator. So we can say the system, this unfavorable system, okay, is perturbed by these potentials, and this unharmonic oscillator is the unperturbed system, and these ideals solvable Schrödinger equations, okay, is the this is the perturbed systems, okay. This ideal system, okay, is the unperturbed system. Okay. When we perturb this with cubic potentials, okay, we can say this system is the perturbed system. Okay. So now we want to know, what is this E, the energy? What is this psi? In relations with this solvable Schrödinger equation, with this wave function, these known wave functions, because we can solve this one, and known energy. So using these two informations of this known energy and known wave functions, we want to get this psi, the approximate wave function and the approximate energy. Okay. Provided that we know this one. Okay. The true, the ideals, the exact wave functions, the true, the ideal or the exact energy you learn in physical 1 and physical 3. Okay. If you know this, you will know this one. So the problem now, how to solve this unsolved Schrodinger equation? Mathematically, we can do this, and what we are learning here, we want to approximate this second order differential equation using this perturbation theory. Okay, we want to approximate this solution. This Schrodinger equation we can solve, this one we cannot solve. Okay, this Schrodinger equation that we cannot solve, we want to solve this approximately using this perturbation theory. Okay, in order to get the approximate energy and the approximate energy and the approximate wave function using this one. Okay, the exact wave functions or the true wave functions, the ideal wave functions, or the true energy, the exact energy, or the ideal energy here. What you learn in physical 1 and physical 2. Okay. So defining the perturbation. So this is the perturbation. The perturbation here is actually the words perturbation coming from this one. Okay, these definitions. So when you subtract this, okay, Hamiltonian, this perturbs Hamiltonians with this zero, we write here, superscript here, unperturbs Hamiltonian. So we will get this C1. So this C cubic potential is actually our perturbations. Okay. The zero mean here, in physical 1 and physical 2, we only use this Hamiltonian, the ideal Hamiltonian for all the simplest system, one particle, this non-interacting one particle system, like a one particle in one dimensional box, one particle in three-dimensional box, okay, one particle harmonic oscillator, one dimension, two dimension, three dimensions, the hydrogen-like atoms, okay, all this system only have one particles, like hydrogen-like atoms, one nucleus and one electron. Okay, because of this mass of nucleus is much heavier compared to these electrons, the center of mass of this system is actually at this nucleus. We only consider the motions of electron. Okay, when we add more electron here, okay, there is new interaction here between electron and electron. So because of this interaction, the Schrodinger equation cannot be solved because of these terms in the Hamiltonian operator. Inter-electronics potential energy term in the Hamiltonian operator. So in this case, In terms of perturbation theory, 1R2 is the perturbation, is our perturbation. And what you learn in physical 1 and physical 2 for the hydrogens like atoms, for instance, going to be denoted as unperturbed Hamiltonian operator. We also can call this zero order Hamiltonian. This zero order Hamiltonian. Okay, this is what you learn in physical 1 and physical 2. In this course, what you learn in physical 1 and physical 2, the ideal Hamiltonian, this unperturbed Hamiltonian is going to be H0. You must, okay, please keep in your mind that what you learn in physical 1 and physical 2 going to be H0. Because we want to distinguish this with the Hamiltonian operator for the perturbed system. This perturbed Hamiltonian's operator. So we use these different symbols, okay, instead of this, okay, H, we write it as H0. Okay, the zero order or the unperturbed Hamiltonian's operator. So now, okay, this perturbed Hamiltonian's operator is the zero order plus the perturbations. Okay, so this is the zero order. So the zero order, this is the zero order. So this is the perturbation. This is what you learn in physical 1 and 2, zero order. So we can include this parameter lambda. Okay, ranging from 0 to 1. Okay, if there is no perturbation, the lambda here to be 0. When we turn off the perturbation, when we fully on the perturbation here, we have lambda here equals 1. So when lambda equals 1, that's what we got here. Okay, we turn off, fully turn on this perturbation. So now we are going to look this, how we can find this psi E here in terms of this psi 0, the unperturbed wave functions and the unperturbed energy. This one and this one in terms of these two known value or known functions. Okay, so we have here two kinds of perturbation: the non-degenerate perturbation, and another one is the degenerate perturbation theory. In general, the degenerate perturbation theory, can be reduced to this non-degenerate. In other words, if you know, okay, the form of this formula or expressions for the degenerate perturbation theory, you can find that the non-degenerates, you can, okay, work out on this non-degenerates perturbation theory, okay, from the degenerate one here. Okay, so general formula or equations for the degenerate perturbation theory can be used for the non-degenerate. like what we done for linear trial functions. Okay, going back to this topic. Okay. Starting from this one basis function, linear variational function, we have only one basis function with this denomination constant. We generalize this. Okay. So this generalizations of the trial function in terms of this n linear combination of basis function, we can show this formula. For instance, if we have here one basis function, only one basis function, we can construct one by one matrix. With this approximate energy. This is one by one matrix. One basis function, we only have one equation, linear homogeneous equation, with the non-trivial solution is one by one circular determinants. So this one is H11 and S11, which is F1, the Hamiltonian operator, F1, d tau, F this complex conjugate of F1, complex conjugate of F1, F1 d tau. Okay, so this one, we only have here one basis functions. This formula can be here compared with this one. This one. For the unnormalized functions. So this is our W, the approximate energy, which the must be here greater or equal than the true energy. Okay. So we have here proof here through these generalizations of trial function in terms of linear combinations of basis functions, having here only one basis function. Okay, we can get this formula. Okay, we can get back this formula. Okay. Likewise for this perturbation. If you know the degenerate form of perturbation theory, we can get this non-degenerate perturbation theory. Okay. When we want to apply here this degenerate perturbation, the non-degenerate perturbation theory, and when we want to use this degenerate perturbation theory. For examples, for this helium, okay, heliums, atoms, the simplest interactings, many electron atoms, or real systems with the many electron atoms or molecules in our universe. Okay. So we have You learn in physical 1, organic, inorganic, how you can place these two electron in the lower state, 1s1, 1s2, using these hydrogen-like atoms. The electronic configurations can be written like this one with this energy. And you have this another energy, 2s and 2p. Okay? X or Y or Z here. Okay. You can see here, when we place these two electrons in this lower state, these two electrons, they are non-degenerates. These two electrons have this non-degenerate energy, which means these two electrons have same energy, but different wave functions. You learn in physical 1. In quantum mechanics, the non-degenerates means when two particles or two systems have same energy but different wave functions. Meaning that here, these two electrons have same energy but different orientations for these two electrons in space around a nucleus. Okay, so the difference here is only the spin orientations, where the spin up and spin down here. Okay, the spin up and the spin down here. So we have this spatial part of the wave functions, the hydrogen-like orbitals, time the spatial parts, spin parts, alpha or beta. Okay, now the non-degenerate here, we can use this non-degenerate. Okay, how about when we promote one electron to higher state? Sorry, not this one. One electron to higher state. Either this one, or this one, or this one, or this one. So the electron could be here, or here, or here, or here. And these two electrons are no longer here having same energy. Electron 1 could be here, has this energy, or electron 2 could be has this energy. Electron 2 could be this with this energy. Electron 1 could be this energy, because these two electrons, they are identical particles. Okay, we cannot distinguish these two electrons. We are not able to distinguish this. So we can say this electron could be electron 1 or electron 2, or this promoted one, this electron could be electron 1 or 2. Because this energy, they are degenerate. This electron 1 or 2 could be here, or here, or here, or here. Because this energy depends only on this n quantum number. The total energy with this n1 and 2 will be the same. n1 and 2 here will be the same. n1 and 2 here will be the same. n1 and 2 here will be the same. So we need this degenerate perturbation theory, because the degeneracy here the 4 false degeneracy here we have, okay, when we promote this electron into this 4 degenerate state. So for the non-degenerate perturbation theory, okay, now we are going to start with these definitions. Okay, you've seen this one. The Hamiltonian operator is the sum of these unperturbed or the zero order Hamiltonians, okay, and perturbations. Okay, for the for the helium, this perturbation is R12, the inter-electronic repulsion potentials. Okay, now we want to know this. This is our problem. We want to know this form. This is, okay, what we are going to solve. So we can write this psi, okay, psi here as a function of this coordinate, okay, and this parameter. And this energy is only on this parameter. Because this energy, we can write here, this energy is only a value, the eigenvalue. So this side, you will write this in terms of coordinates. Q here in Cartesian coordinates, okay, whether in 1 dimensions or 2 dimensions or 3 dimensions here. Okay. So now, okay, now we can expand this in terms of Taylor series. Okay, I skip this derivations. You can, okay, expand this in terms of Taylor series, and this as well. Okay, Taylor series, and this is the final form of the wave function we want to find. Okay, using the unperturbed, oh, okay, wave functions, these known wave functions. Okay, this one. Okay, so we must know this in order to solve this one. Okay, and we already know this. Okay, this function and this energy from the solution of the exact Schrödinger equation. This, okay, the solution of this exact Schrödinger equation, this one. So when we expand this in terms of Taylor series, we have this. You can see here clearly. So this is the zero order. You must know this one. And you have this unperturbed of the zero order energy and this one. Okay, for your levels, okay, this physical 3 course, you only learn up to this first order correction to the wave functions and first order correction to this energy. Okay, for more advanced course, okay, you can find this second order up to this more here higher order corrections to the wave functions, higher order correction to the energy. So it means for the K here, we call this as K order correction to these wave functions and K order correction to this energy. Okay, you will learn up to this first on the only. So now we are going to find this first order correction to the wave function. Okay, using this also information from this unperturbed wave function, this unperturbed energy. And you can write this psi 1, the first order correction to this wave function and first order correction to this energy, in terms of this one, this one. Okay, psi 1 here, E1 here in terms of psi 0. This one and this one in terms of psi 0. And also the manipulations, the derivations, okay, is very tedious and quite lengthy. You can prove this. The first order energy correction is actually the average or the expectation value of perturbations. So now you can see here how we use this zero order wave function to write this E1 in terms of zero order wave functions. And the perturbation. So we know this, initially we know this, we already know this for this particle, for the hydrogen atom is R12. For the n-harmonic oscillator, okay, I shown this one, the cubics, for example, we use this, cubic potentials. So this is our perturbation. We know this perturbation, we know this one, the zero order or the unperturbed wave function, this ideal wave function you learn in physical 1 and physical 2. We will know this first order energy corrections, and you know the first order energy corrections, of course, you will know this approximate energy. This is the approximate energy. Okay, and also this one, so you can write using only the first order energy corrections. Okay, so this is the final formula you can use. Okay, this is for the non-degenerate perturbation theory. Using the degenerate perturbation theory, this one, perturbation theory, the degenerate one, you can prove, okay, this formula, you can get back this formula from the degenerate perturbation theory. This E, the approximate energy. Okay, and this also for the first order energy corrections to this wave function, we can write this in terms of zero order and the zero order energy. Okay, sorry, I forgot to this one. Okay, so this one and this zero order energy. Okay, zero order energy. So if you have this, if you want to determine, okay, sum over all the unperturbed overlap of this N1, N2, N3 for the non-degenerate energy and the difference here between each of this energy all possible different of this energy. Sorry. Okay. Now we can write this approximate energy, okay, to be zero order plus this first order energy corrections. Okay. So you can see here, this is only the approximations E, and this also psi here, only the approximations. Now we are going to look these examples, the ground state helium. Okay, so the ground state helium's atom here, we know this complete Hamiltonian operator, the non-relativistic Hamiltonian operator, which only depend on this spatial coordinate. This is spatial coordinate. This is spatial coordinate. Non-relativistics, when we here, okay, do not consider the interaction between electrons with velocity of electrons close to the velocity of light, okay, due to the interaction between these two electron repulsion between electrons. So this is a non-relativistic Hamiltonian operator. So the wave function here, okay, as the function of these two electrons coordinates in spherical polar coordinates. Because of these terms, the potential and the repulsion, the Schrödinger equation cannot be solved. So this is a charged electron, second electron, okay, this is first electron. Let's say this is first electron. So now we want to treat independently, separately, these two systems. The first hydrogen-like atoms and the second hydrogen-like atoms. Okay, so this is the step involved. We want to solve this helium ground state energy by separating this into two hydrogen-like system. So this is the hydrogen-like system. The first hydrogen, this is the second hydrogen. So we know each of these you learn in physical one. The first hydrogen, okay, has this energy, the zero order, and the second hydrogen-like atom here, okay, this is the second hydrogen-like atoms with charge positive 2e, okay, which only here has only one electron, and this is the second energy, the zero order or the unperturbed energy. So the total unperturbed energy will be you can prove this, okay, because the Hamiltonian operator here is the sum of the zero order, this one, the first Hamiltonians, the zero order or the hydrogens likes or the unperturbed, the hydrogen like Hamiltonian operator. This is plus perturbation. So this is perturbation. This is the perturbation. So this is the second hydrogen-like atoms. You learn in physical ones, okay, the principles of quantum mechanics. When we write this sum of the two Hamiltonians, we can prove the energy is actually the sum of these individuals' energy. Okay, resulting, okay, from this solution of individual Schrodinger equations. So the wave function here, so this is 0. And this as well for the H2. This second unperturbed Hamiltonian operator. So we can prove this sum of this Hamiltonian operator will give the total energy here will be this sum of these two individuals hydrogen-like energy, E1 and E2. This one and this one. And we can prove, okay, the zero order is actually a product of these two individuals hydrogen like wave functions or orbitals. Okay, this is what you learn in physical 1. Okay, the energy and the wave functions, the products. So as I mentioned earlier, you can see here, H here is the sum of these two hydrogen-like Hamiltonian operators. So you can write like this form. So, and the product here, okay, from this solution of two individual Schrodinger equations for hydrogen-like atoms. Okay. Now we have this one, okay, this formula, okay, this actually the zero order, and this as well the zero order. Okay. Now, in atomic unit, you can set this as 1. This E prime here we define as discharge 4,5 this vacuum permittivity. Okay, this is how we define this E prime. So now we have here this also the Bohr radius here in atomic units for length is 1. Okay, left only here in atomic unit. Okay, so Z here, number of protons, this over 2 plus 1, this 1, okay, state 1 and state 2. Okay, both here 2 electron in the lower state 1s, so this is 1, and the second electron here, this is 2. And for electron 2 and for the electron 1, so we'll get this zero order from this one. And the wave function here is the hydrogen-like wave functions. For electron 1, as a function of this electron, we're numbering this electron as electron 1 and electron 2. Okay, so this is the zero order. Wave function or the hydrogen-like function for electron 2. So this is what we get. Okay, So you can solve this. This number of proton here is 2. So this is 1 in atomic unit. So this is 1 in atomic unit. Okay. You can also convert the atomic units to the electron volts. Okay, this when we consider is this value and this Bohr radius, so we can write this energy in electron volts. So this is our problems. The main problem here because of this E1. So we know this zero order. We know this zero order. The zero order is what? This one. Zero order wave functions. Okay, now we have these wave functions. So we have these triple integrals. This is for the electron 1. This is for the electron 2. For the first triple integral for the electron 1, so we have this second triple integral for the electron 2. This over these volume elements. Okay, you can prove this using Jacobian. You learn in mathematics asas. Electron 1, electron 1. So this is electron 1. This is electron 1. So this is the electron 1. Okay, we have these triple integrals. So basically, this is what we are going to solve. Sorry.
Excuse me, doctor.
R1, yes.
It's already 10:16 and I think some people have class.
Okay, now we stop here. Okay, so we can stop now. Okay, now I will leave this, okay, as your homework if you want to. Okay, to obtain this E1. Okay, so now we can stop here. Please take this. I think you can use this for your attendance. Okay. Now